Okay, so as an application to trees, we'll talk about spanning trees. So if we have a connected graph like this one, we can create a spanning tree for this. So for this graph, I'll name the vertices A, B, C, D, E, F, G, H, and we want to have a spanning tree. Now a spanning tree is a subgraph of the graph that contains all the vertices of the original graph and is itself a tree. So for a small graph like this, you can figure out spanning trees pretty easily. We start with A. We could say adjoin everything connected to A, B, C, and G. And that's a tree. From C, we can pick up D and E. And then from, let's see, we've got A, B, C, D, E. We need F and H. And from D, we can pick up F. And from B, we can pick up H. So there's all of my vertices. 1, 2, 3, 8 of them in a tree. Why this is useful? Well, if these are nodes represent things that you need to, I don't know, a bunch of processors that you need to check. This gives you a way to check them. Start at A, check that one, check everything connected to A. And then once you're at B, check H. Once you're at C, check D and E. And then you can check F, and it gives you a way to organize these things, how you check them. So that's one way to build a spanning tree. Another spanning tree would be to start at A and just sort of work your way through the graph. A to B to H, so go A, B, H, and then I can go F, E, G, F, E, G. Once I'm at G, I can't go back to A because that's already on my list. I can't go back to H because that's already on my list. But if I'm at E, I can pick up C as well. Oops, C. 1, 2, 3, 4, 5, 6, 7. What's the one that I'm missing? A, B, H, F, E, G, and from F. Oh, and from C we can go over to D, and that gives me the whole list. So a couple different spanning trees. Why is it called a spanning tree? Well, if we take this one, we could take this and say, okay, we started at A, we included B, C, and G. From B, we include H. From C, we included D and E. And from D, we included F. Right. And so there in red is our spanning tree. Every vertex is listed. Every vertex is in the spanning tree, and there's no circuits or anything. So that's a spanning tree. Small graphs, you can do this just by sort of looking at them. If we have larger graphs, I'm going to zoom out a tad. Like 1 million vertices and 1 million edges, how do you find a spanning tree? So there's 2 different ways to write algorithms to do this. The depth first and the breadth first. Depth first is algorithm 9.3.7 in the book. And breadth first is algorithm 9.36. So we'll do the depth first algorithm to find a spanning tree for this graph, which is a slightly larger graph than the other one. I'll misplace my pen, there it is. So algorithms start with an order. We have an order for our vertices, A, B, C, D, E, F, G, F, A, B, D, G, E, F, C. A is highest, C is lowest. So if you're writing an algorithm, if you want to program a computer to do this, you have to tell it where to start and where to go. So depth first says, I'm going to list, oops, 5 and options. Where do you start? So you start at the highest ordered one, right? So we start at A. What are the options to go from A? Well, whatever vertices are connected to it. So we started at A, and what are the options from A? You could go to B, you can go down to D, you can go down to G, a lot of options from A, you can go down to F, you can go down to E. So we're telling our program to find a tree. It's starting here. Where does it go? The next place to go is, out of all the options you have, go to the next highest rated one. So of all my options, what's the next highest rated? That's B. And so, rolled under the B. So now our program is sitting at B. What are the options that the program sees from B? Well, it sees D, it sees E, and it sees C. B is connected to A, but A we've already visited, right? So you can't go back to A. Right? A tree has no loops in it. So where does it go? It's sitting at B, and it says, okay, out of my options at B, which one's the highest rated? And that would be D. So it goes to D. So now it's sitting at D. Oh, as I do this, right, B has been used. It's no longer an option. Now we've used D, so that's no longer an option. We'll cross that out there. We're sitting at D. What are the options at D? The options at D are C, G, and E, right? Not including A and B because we've already been to those. So sitting at D, what's the highest rated of your three possible options? So C, G, and E. G is the highest rated. So we go to G. Now we're sitting at G. G is no longer an option, so we cross it off here. We can cross it off here. You can see how this is going. You go to a new vertex. You list all the possible options that you can go to. And G, you can go to F and E. And you look for the highest possible option that you have at that particular vertex. So C, F, and E. E is the highest rated. So we go to E. And we go from G to E. And then we cross it off as an option anywhere like that. So now we're sitting at E. What are the options that we have for E? You don't have D, you don't have B, you don't have A, you just have F is the only option from E that hasn't already been visited. So you go from E and you go to F. So F is where we are, that's our live one. We cross off the F's anywhere because those are no longer options, and we sit there and say, okay, we're sitting at F. What's our possibilities? Well, there's nowhere you can go to from F. There's no options. So we haven't completed our tree yet, though, because we haven't been to C. So you do what's called backtracking. You're sitting at F. You backtrack to the last place that you had an option. E, no options available there. If you get back to G, though, you do have an option. You can go to C. So you take that option. You say, okay, we'll go up to C from G. So when your algorithm gets stuck, you tell it, go back. And now we're done because we've got all of our vertices on our graph. So what kind of a tree did we actually build? We started with A, we went to B, we went to D, G, E, oops, E, F, and then off of G, we went to C. So there's our tree, sort of written as a tree. And it's depth first, and that creates kind of a very deep tree, but with not so many branching. Okay, so that's one way to do it. You just sort of, to find a search tree, you can program computers to do this, is given a graph, give it the list of vertices in a particular order. Say start at the first one, see what options there are, go to the highest ordered option, keep working way down until you've exhausted the list, right? And once it got to C, it knows that it's got all of the vertices on its list. So, oops. Here's the same graph. what's the breadth first algorithm? We'll do it twice. Breadth first is a little bit different because instead of saying, well, it starts off the same. We start off with A, and that gives you your options are B, E, G, E, and F. Okay. The difference between breadth first and depth first is that when you are doing breadth first, you take your vertex where you start, A, and you just add all the options all at once. So B, D, G, E, and oops, we'll put E down here a little bit, and F. So there's our start of our tree. Right? We just put on all the options. So now I have 5 different places to go because I haven't gotten all my vertices on there yet. I've got 1, 2, 3, 4, 5, 6 vertices, and there's 1, 2, 3, 4, 5, 6, 7 possibilities. So where do I go next? Same idea, right? I look for the highest ranked option, right? These are all my terminal vertices, right? So I look for the highest ranked terminal vertex, that's B. And I go to B and I see, well, what are the other options that I have available? From B, I've got A, but that's already on the graph. I've got D, that's already on the graph. I've got E, that's already on the, well, not the graph, on the tree. And I've got C, that's my other option. So then we put on C to B, and now we have a tree, right? And that's got all of our vertices on it. So there's a breadth first. And so it doesn't have much height, but because we add all the vertices all at once, then that gives us a very wide, broad tree. Right? If you compare it to the other search tree that we got from the depth first, this is high depth because it goes down a long way from A to F. This one only has a height of 2, right? A to C. So this one's broad, this one's deep. So you can find different search trees. Not search trees. You can find different spanning trees depending on what your order on it is. If you start this order and we do that, right? And I'll just color this one in red. It says start at C. What do we do with the breadth first algorithm? We color in and connect all the vertices connected to C. So now I've got B, D, and G as 3 possible places to choose as my next live one. What's the highest rated of those? Out of B, D, and G, the highest rated is G. So I go to G and I connect everything that G is connected to. That's G and E. That's not already in the tree. So what are the places that I have left? I've got B, D. Oh, and we can connect A to G. There we go. So what are the places that we have as terminal vertices? B, D, A, F, and E. And that's everything, right? 1, 2, 3, 4, 5, 6, 7. So we've got the entire graph there. So that gives us that breadth first algorithm. We started with C. From C, we added B, D, and G. And from G, we added A, F, and E. That gives us a different spanning tree. So there's lots of possible spanning trees depending on how you order your vertices and whether you do, so here's, well, there's 2 anyway. You can get different spanning trees depending on whether you just join all the vertices all at once, which is the breadth first, which is what that is, or if you just start at a point and just follow your way through the graph, and that's the depth first algorithm.